All right, everyone. So we're going to get started on our nuclear chemistry notes. They are sideways paper. They say nuclear chemistry notes on them, and they look like this right here. So once you have those ready, we can go ahead and get started. So the first question is asking us, what does nuclear energy have to do with the electromagnetic spectrum? And you can go ahead and pause the video and read through A through D and see which one is the best answer choice. So once you read through them, what we should find is that the correct answer is letter C. It says energy released in a nuclear reaction is shown on the electromagnetic spectrum. So that is the best answer for this question here. And we can see that on the very right-hand side of our electromagnetic spectrum is the nuclear energy that we're going to be talking about. So we can see that it's very small. So this is the first few things that we're going to write down. Go ahead and write down the letters that are in red. You can pause the video if you need more time to do that. So electromagnetic radiation is defined as energy that travels through space. So whenever energy is traveling through space to reach its destination, that is electromagnetic radiation. So examples include the light from the sun. So the light from the sun obviously is has to travel through space a great distance to reach us here on Earth, right? So that it falls under the category of electromagnetic radiation. So for the next bullet, whenever you're cooking or you're heating up food in the microwave oven, you stick your plate in the microwave and the microwaves stem from the oven itself to your food, right? So the energy travels through space to reach its destination. Same thing with x-rays. If you ever had x-rays done, the x-rays travel through space to reach the part of your body that you need scanned. Heat from a fireplace also has to travel through space to reach you, right? To get the heat from the fireplace, you don't have to insert yourself directly into the fire. The heat travels through space to reach your hands or to reach your body to warm you up. And then, of course, the gamma rays produced from radioactive decay. So you can go ahead and pause if you need time to fill in the words that are in red. But next up, we have radiation. Radiation it's defined as rays or particles that are given off by an unstable nucleus. And these rays and particles are able to go through things. That is what radiation is defined as. Okay, so next up, we have a few pictures. We're going to think to ourselves whether these images are examples of stability. Basically, if they're stable, we are going to circle the word stable on our notes. If they are unstable, we're circling the word unstable, right? So first up, we have the Leaning Tower of Pisa. So I wouldn't feel too confident about climbing up to the very tippy top of the Leaning Tower of Pisa. So I would say that this is unstable. We have a rock formation here. I would not want to be standing next to that rock, right? Just in case it could fall over. It looks pretty slanted. So I would say that this rock formation is unstable. And then last up, we have our sleeping kitten. That looks pretty stable to me. So we would circle stable for the sleeping kitten. Next up, we're going to think to ourselves, what does unstable mean? Because we were able to determine which one was stable and unstable, right? So what is our own definition of unstable? And we have a section in our notes where we can write down that definition. So go ahead and pause the video and you can write down your definition in your notes. All right, next up, we have a video. Let me make sure I'm sharing my sound here. There we go.
Our brain's response to the word radioactivity usually takes us into the realm of superheroes or into some dark, reimagined, post-apocalyptic world after a nuclear fallout. There is rarely a middle ground. However, 120 years ago, the world had a completely different perception of radioactivity. In fact, It was considered to be a miraculous reservoir of health and vitality. From toothpaste and watch dials to water and butter, radioactivity was everywhere. So, what happened? How has this marvelous discovery, which was considered one of humankind's greatest achievements, turned into something that scares countless people across the globe? Well, let's start with the basics. Everything we see around us is composed of elements with stable atoms. The subatomic component responsible for maintaining the stability of an atom is called the nucleus. Now, imagine that you're about to sneeze, but it hasn't quite come out yet. How does that feel? It might be strange to describe, but that's exactly what certain atoms experience all the time: the urge to expel the excess and regain stability. Inside an atom's nucleus, there are positively charged protons and neutral neutrons. These nucleons are held together by a glue called the strong nuclear force. This strong force cancels out the repulsive electrostatic force of like-charged protons and keeps the nucleus stable. The nuclear force has a short range of action and is dependent on the ratio of neutrons and protons present in a nucleus. However, we see that the balance between the forces starts to waver in a nucleus where the number of neutrons exceeds the number of protons. A nucleus that exceeds the threshold number of neutrons and protons that the strong nuclear force can hold together comfortably will become more unstable. More specifically, these scenarios give rise to unstable isotopes of elements. Just as your body, through a series of expansions and contractions, expels a substance with a sneeze, similarly, the unstable isotopes of elements fling out different particles or forms of energy to restore balance between the forces in their nucleus. During this process of attaining stability, they change into a new nucleus. It is exactly this property, namely turning into something new to attain stability, that we call radioactivity. The process by which it transforms is called radioactive decay.
All right, so then next up, we have the three types of particles that are emitted in order to achieve stability. Like we were seeing in the video, those are alpha, beta, and gamma rays. So for the alpha particles, we will see, or there's two different symbols that we can see. One of them is the alpha symbol, the letter alpha in the Greek alphabet. For beta particles, one of the symbols that we'll see it as is the beta symbol, which is the letter beta on the Greek alphabet. And then last up, gamma rays, of course, the symbol would be gamma, the backwards Y, also a Greek letter from the Greek alphabet. So starting off with the alpha particle is defined as a helium nucleus. And that is because when an alpha particle is emitted from the atom, what is actually emitted is 2 protons and 2 neutrons, which is the same as a helium atom, right? Helium has 2 protons, which 2 protons are emitted during alpha decay. And then it also has 2 neutrons, which would give it a mass of 4, right? 2 plus 2 would give us 4. So that is why we refer to it as a helium nucleus. So it makes sense that the chemical symbol that we use to represent an alpha particle is the same as the chemical symbol that we use to represent helium, right? We have the symbol He for helium. The mass is 4 because of the 2 protons, 2 neutrons. And then the atomic number, the number of protons, is 2. For beta particles, really similar, except not at all, because in this case, electron is being emitted. So for the symbol for beta particle, we have the E for electron, 0 because electrons have no mass, and then -1 for the charge of the electron. So then we have our gamma rays. Gamma rays are actually the most dangerous of the 3 that we're going to talk about. So if you remember, like we just talked about alpha and how it has 2 protons and 2 neutrons, right? So the fact that it has those subatomic particles involved, that's like if you're putting on a lot of coats. If you're putting on coat after coat after coat, it's not going to be that easy to move around. So alpha particles, they don't get very far because of that reason, because they have those 2 protons, 2 neutrons that make them really clunky. So they can go through a lot of different things because they have so many coats on. The beta particle, it doesn't have mass, but it does have a charge. So that slows it down in the sense that it's also not able to go through a whole lot of different things. But gamma rays, they don't have mass, they don't have charge. So they're able to go through a lot of different things, and that makes them the most dangerous for us. This is showing us how easily our particles can go through different things, if that makes sense. So alpha particles, that's the first one. We already said that because of its protons and its neutrons, it's too clunky to go through a whole bunch of different things. So we can see here that the alpha particle is stopped by something as simple as a piece of paper, right? Beta particles, they're a little less clunky because they don't have mass, but because they have charge, they're able to go through paper, but they're not able to pass through a human hand. Gamma, on the other hand, we just said that it has no mass, it has no charge, so it is able to go through a variety of different things. In fact, one of the only things that can stop your gamma rays are lead. I was going to say lead aprons. If you've ever gotten your x-rays done, they put a lead apron over your torso to protect your organs from the radiation. All right, so once again, just a reminder that you can always pause the video if you need more time to write. But the first bullet here, it shows us the difference between a nuclear reaction and a chemical reaction. So, so far, up until now, we've just been talking about chemical reactions. And chemical reactions, they involve changes in the electrons, right? When we were talking about ionic and covalent bonding, it was either a transfer of electrons or a sharing of electrons. That's what happens in chemical reactions. But now today, we're talking about nuclear reactions. And in nuclear reactions, what's changing takes place inside the nucleus. And as we know, or we should know, hopefully by now, electrons are not within the nucleus, right? They exist outside the nucleus within the electron clouds. So nuclear reactions specifically involve changes only within the nucleus of our atom. Nuclear reactions are not affected by changes in temperature or pressure. So changing the temperature or pressure is not going to make it speed up or slow down, which also brings us to the next point, right? Once it starts, once our nuclear reactions start, we cannot change them. We can't speed them up. We can't slow them down. We can't say, you know what, never mind, turn it off. Cannot be done. And nuclear reactions always release a lot of energy so that the atom becomes stable. Here are some symbols that we use in nuclear equations. Most of these we're already familiar with, right? We know the arrow from when we went over balancing chemical equations. So that's our yield symbol. It indicates that the reaction is producing products from the reactants. We have the chemical symbol. The top number is the mass, the bottom number is the number of protons. We see our chemical symbol for the alpha particle, a chemical symbol for the beta particle, and then the gamma, which is kind of cut off, but it is the same as the slide in which we were talking about gamma rays. All right, another video.
Alpha radiation consists of heavy and slowly moving particles with a lot of electrical charge. These properties combine to make them easy to stop. You can stop alpha particles using a single sheet of paper. Here, I'll show you. Here is a sample that emits alpha particles and a Geiger counter. The paper stops the radiation. Beta radiation consists of light and fast-moving particles with electric charge. This means that they can be stopped by reasonably thin plates of material. For instance, we see here that they can be stopped by a thin metal plate. Gamma radiation consists of fast-moving particles with no electric charge. This means they emit no electric fields to interact with matter. They are therefore much harder to stop. To stop gamma rays, you need a heftier chunk of dense material like lead. This is also true for X-rays, which is why they put a lead apron on you when you're getting dental X-rays. Neutron radiation consists of pretty heavy particles with no electric charge. Since they don't interact with atomic electrons, they can travel long distances, say hundreds or even thousands of meters in air. The way to slow them down is not so intuitive. you have to use something with a lot of hydrogen in it, like water or plastic. The neutrons hit the protons in the hydrogen nuclei and knock them out. This stops the neutrons, and then the charged protons are stopped quickly, much like alpha particles are.
All right, I accidentally kept that video running a little too long, so you don't have to worry about neutrons. We're not going to be going over that in this class. So that brings us to alpha decay, right? So that's our backside of our notes. We were asked to write down the equation that is shown, which I wish I could write on it. Hey, I can. I love Zoom. Okay, so you would be copying in this equation into your notes. So once again, you can pause if you need to. But the explanation for what's going on in this equation, because I know that it looks scary, but let's start off at the beginning. So in the beginning of this reaction, we started off with plutonium 240. 240, by the way, is the mass of the atom. 94 is the atomic number, which also is the same as the number of protons, just a refresher in case we forgot. So we start off with plutonium 240. It is unstable. So it undergoes alpha decay. That means it emits an alpha particle in order to become more stable, right? So when it emits an alpha particle, it's getting rid of 2 protons and 2 neutrons. So there, of course, is our symbol for the alpha particle. So let's say we have, all we know is what we start off with, and we know that it undergoes alpha decay, right? If we take 240 and we think to ourselves, well, plutonium emitted 4 from its mass. So 240 minus 4 gives us 236. So we can figure out the mass of the new atom. Then we take our number of protons, right? 94 is what we started off with. But when it emitted an alpha particle, it lost 2 protons. So 94 minus 2 gives us 92. Remember that no 2 atoms have the same number of protons. So once we figure out the atomic number, all we have to do is reference our periodic table and think to ourselves, all right, well, which atom is atomic number 92? And that's uranium. Once we find out the identity of the atom, that's it, we're done with figuring out the equation. So next up, we have a little bit of practice, and I'm just realizing, oh, I can write on this, yay. Here, clear all drawings. So it says that we're starting off with sulfur, and I'm thinking I'm going to have to draw in the numbers. So it's sulfur with the mass of 37. Ooh, this is going to be difficult. So there's my mass. Sulfur, if we look up at the periodic table, it's number 16. So there is my atomic number. Forgive the messiness. So then I have my yield symbol or something like it. And I also know that alpha decay happened, right? So we have our symbol for alpha decay, and we need our little numbers as well. That was 4, our mass of 4, and our atomic number of 2. So all that's left is to figure out which atom we end up with. And I just realized that I could have just used the text feature to do all of this. But anyways, let's look at our mass first. So we started off with 37, but we emitted 4 of the 37. We lost 4 of the 37. So 37 minus 4 is 33. For our protons, we started off with 16, but we emitted or gave off 2 with that alpha particle. So 16 minus 2 is 14. So once we figure out the number of protons, which was 14, we're going to look at the periodic table. Mine's over here. So number 14 is silicon. So my symbol is Si. And that is it. That is our finished equation. And we can do the next one as well, which is iridium. So we're starting off with IR for iridium. Its mass, it said, was 174. So I'm going to put the 174 up at the top. And if we look at our periodic table, the atomic number of iridium is 77. So I'm going to put that at the bottom, 77. All right. So iridium undergoes alpha decay. That means that it emits an alpha particle. So I'm going to fill in that portion of my equation. We have He with a mass of 4, and you can speed me up if you need to. And then a atomic number of 2, of course. Ooh, that does not look good. I can't move it. Oh well. So then the last thing again is to figure out what goes in this spot right here. And you can pause the video and try to figure it out for yourself. It would be a really, really good practice. So I would think to myself, 174 minus 4 gives me 170 for my mass, for my new mass. And then 77 minus 2 gives me 75 for my new atomic number. So then we would reference our periodic table again and look for number 75. This would be Re, capital R, lowercase e. So that is our final answer. So then we can talk about beta decay. So beta decay is really similar, except there's a little trick to it. So when an atom loses an electron, it emits an electron from the nucleus. That is beta decay. What results from this is that a neutron becomes a proton. So instead of subtracting from the original atomic number, we're going to have to add. So let's look at this. We start off with cesium. And cesium has a mass of 137. It emits a beta particle, right? So remember that beta particles do not have mass. So 137 minus 0 still gives us 137 for a new atom. The tricky part comes with the atomic number. So it says that a neutron becomes a proton. So we increase its atomic number by 1. So the way that I think of it is 55 minus -1 would result in you adding on 1, right? Which would give you 56, and atomic number 56 is barium. So that's a little trick, is that instead of subtracting for your beta decay, you're going to have to add on 1 to the atomic number. And of course, we have practice. So for our text, okay, we start off with platinum 199. So we have a mass of 199. Platinum is number 78. So I'm going to put that down at the bottom. And the symbol for platinum is PT. So then we have our arrow. And we know that a beta particle is emitted. So that needs to be included in our equation. So this time, we're going to have 0 up at the top. And down at the bottom, we should have -1. And our symbol would be the letter E. There we go, kind of, sort of. Not very pretty, but there it is. So 199 minus 0 gives us 199. 78 plus 1, or minus -1, if you want to make it a little bit more complicated like I do, would give us 79. So atom number 79 is Au, gold. And you can try to figure out the last one on your own. I have the answer on the next slide so that you can check your work. There it is. And now we have gamma radiation. So when we're looking at these equations, we're not going to focus on gamma radiation at all. The only thing that you need to know is that there's no mass and there's no charge, but gamma radiation is emitted along with an alpha or beta particle. So you can see in this equation, this was plutonium and it underwent alpha decay, right? It emitted an alpha particle. We can see that through the He. But along with that alpha particle, gamma radiation was emitted, which we see shown here in through the gamma, the letter gamma in the equation. Okay, so that brings us to nuclear fission and fusion. So again, you can pause the video if you need to write down the notes, or you need extra time to write down the notes. So fission and fusion are opposites of each other. In fission, you start off with a large nucleus, and this large nucleus is unstable. So in order to become more stable, it splits into 2 smaller, lighter nuclei. So the smaller nuclei that result from this are more stable than the original, which is the point. Fusion is the opposite, right? We have two smaller nuclei and they fuse together to form one larger nucleus.
Have you ever been in an argument about nuclear power? We have, and we found it frustrating and confusing, so let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a peaceful spin-off of the new technology, helping the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain, the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal, and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finest hour finally came in the early 1970s when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day, the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade, though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy? The pro and contra arguments will be presented here next week. Subscribe, and then you won't miss it.
All right, so for nuclear fission, we start off with a heavy nucleus, one heavy nucleus, and it splits into a more stable form. So we start off with one and it'll split into two. And as it goes on, we have more and more splitting happening. So it makes sense that it started off because our nucleus was too massive, right? So it makes sense that what we end up with after it splits is less massive than what we started off with, right? That was the whole purpose of fission. And a lot of energy is released. So a chain reaction, this is specific to fission reactions. So if we see, I hope I can zoom in. Nope. If we see very, very tiny in this picture, we have a gray neutron, and this neutron hits our uranium atom. And what happens is it split the atom. Right now we have two. So more neutrons are emitted, and this splits our atoms further and further, and it goes on and on and on in a chain reaction, right? So this releases a lot of energy and heat that produces an atomic explosion. So I have an animation here for you, and I wish I could speed it up. But there's our nucleus. We have our neutron hitting. So the fission separates the uranium nucleus into two atoms. And we also have energy being produced as a result. And the chain continues, right? So fission is used to produce energy specifically in power plants. So because the whole chain reaction thing is happening within your nuclear power plants, you have these control rods that are installed in order to slow down the chain reaction, because otherwise it could get a little out of control.
Of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now it costs more energy to do the experiments than they produce in fusion. The technology has a long way to go before it's commercially viable. And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it will be so efficient.
All right, so for fusion, the opposite of fission, we have two nuclei, fusing to make one heavier nucleus. So this produces more energy than fission does, and it's a source of energy for the H-bomb, which is not the atomic bomb. It's actually 1,000 times or thousands of times more powerful than the atomic bomb. It's the most destructive force on the planet. So we have a little learning check. This is our last slide. Go ahead and pause the video, see if you can figure it out for yourself. And you can check your answers in 3, 2, 1. There you go. So you can check your work. And that's it for our notes. But I know that you also have a worksheet to go along with it. So this worksheet looks like this. This is one of the sides. I want to say it's the front. This is the 140 versus 141. Yeah, so this is the front. It says radioactivity. And then the back says comparing nuclear fission and fusion. So this is what we're going to do together, this side, the back side. So hopefully you know the difference well enough to be able to give a description of the process. So for nuclear fission, that is one nucleus splitting into two. And then, of course, fusion would be the opposite. You start off with two nuclei, two smaller nuclei, join to form one. What is produced as a result? Well, they both produce a lot of energy. So that is going to be the first thing I write down, lots of energy. You also have neutrons and radioactive isotopes. For nuclear fusion, there we go, kind of. We also have lots of energy and neutrons, but not so much the radioactive isotopes. So that brings us to the next point, right? Are the products radioactive? For nuclear fission, that would be a yes. Often they are radioactive. And for fusion, that would be not really. So we put not usually for fission. Sorry, for fusion. What is needed for this nuclear reaction to occur? So for fission, we need a neutron to start the chain reaction. Neutron singular, and then for fusion we need high temperature and pressure. Where does it occur? For fission, we have our nuclear reactors and the atom bombs. Okay. Then for our fusion, it occurs within stars and our sun, which is a star. And then we also have hydrogen bombs. And then we don't have to worry about the given example of a nuclear equation. We can just leave that blank and that's okay. So then for number 2, we have 2 pictures and we have to decide which is fission, which is fusion. We have to label the parent isotope. So that's what we start off with, what we end up with, where the neutrons are, and the energy. So letter A, if we look at it, we start off with our proton-neutron fuse, right? And then we have our end products here. So this is fusion. Fusion. So the parent isotopes would be the 2 parent isotopes. would be the two that are here on the left-hand side, 1, 2. And then our daughter isotope or the product is over here on the right-hand side. And in the middle, we would just label that this is fusion/energy. There we go, kind of. For B, this, of course, if it's not fusion, it'll be fission. There we go. Fission. So we see our neutron here that starts the reaction, the chain reaction, neutron. We see our parent isotope, which is this bundle right here. So I'm gonna label it underneath, parent isotope. That's what we start off with. Then we have our daughter isotopes, which are here. And we have more neutrons. These 1, 2, 3 little loners here are more neutrons. And then we have fission, the energy. All right, so that was the back side. So you are still responsible for the front side, which is just vocabulary. There are some like CANDU reactor, induced an isotope, I believe, that we don't have the official definitions for, but I'm gonna go ahead and give you something to reference, or I guess I could tell you where those go. I think that's a better idea. So we said the CANDU reactor, that one's actually number 10. The Canadian deuterium uranium reactor, so CANDU reactor. Induced would be number 6. A nuclear reaction is induced or started by bombarding a nucleus with alpha particles, beta particles, or gamma rays. And then we also said isotope, right? So that one's part of number 4. Atoms are changed from one isotope to another. Isotope. There's also 2 tricky ones here. Number 7, that would be proton. Number 8 would be neutron. There we go. Neutron. And you should be able to do the rest on your own.